Iterative versus recursive methods. Tree is a recursive data structure. We can recurse into each tree's node from the very top, which is root, all the way down to either the left or right, sometimes both. The question here is whether we should iteratively go through our set of nodes, or should we write a recursion for it? Breadth first search or breadth first traversal, and the other one is a depth first. One involves level order traversal, visiting all of the nodes horizontally. And the other one is depth first. It goes down and then back up and then goes down and back up. That's the difference between the two of these. Every time you see a while loop, for loop, these are actually the iterative methods. The recursion is a lot simpler. We use recursion, as you saw, in binary tree traversal, either in order, post order, or pre-order. Those are recursive. Every time we're dealing with iterative mechanism, we can convert it into recursion and vice versa. So it doesn't really matter which one to use, but we're going to compare the two in this 7.5 subchapters and see which one has more merit over the other. Specifically, we're going to look at our size method, right? So this size method computes the number of nodes. If this is your tree, the size of the tree here is 4 nodes. Let's say if you add another one, you add another one here, and the size of the tree is 6. We're going to write a recursive algorithms in place to find out the size of the tree. We also look at how we can use iterative methods to compute the size of the tree. And then we'll do comparisons after that. So here's the recursion. Because a tree has both left and right subtrees, in order to set up our recursion, we want to have a placeholder. This is kind of our placeholder wrapper that wraps around the recursion size algorithms. And this recursion size is called recursive call. This is the call that's going to be called upon over and over again, right? Depends on what your entry is. The number of nodes in a tree is 1 plus the number of nodes in the left subtree plus the number of nodes in the right subtree. So generally speaking, you have something like this. This tree branches off to more branches. Very first top is what we call root prime. Okay, that is a 1 right there. When you add up all of the nodes from the left to what's on the right, plus 1. So this is what's on the left, and this is what's on the right, plus that 1 right there. We have the total number of nodes in the tree. This is the formula that we're going to abide by, and let's write some code and see what that looks like. And this is the recursive size. It returns an integer. This integer is the number of nodes you have in this tree. Your recursion can look like this. At every step of the way, it's checking to see if node get left is null, if node get right is null. If that's the case, then return 1. That 1 right there is your inner node. Your inner node is by the time you recurse into this point. Let's say this is root prime, R prime. This product could be the inner node as well. That's 1 right there. If both of them are null, right, there's nothing to go with, then that node itself is 1. So you return 1 basically at the very end. That 1 right there represents a leave. Otherwise, return 1 plus rect size all the way to the left plus rect size all the way to the right. We're not checking to see if node point is null or not. So this is going to get into the issue when you have node get left. So we have to do something, right? Checking to see if node is null or not. This is not a good idea. This is going to crash in some edge cases when null is null. So let's approach this from a second version standpoint. Now we're checking to see null is null or not. So that sounds kind of good, because if null is null, then return 0. Otherwise, checking to see if this returns 1. I would argue that this part is not as efficient. And that is because why would you have to check if the left is null and then right, the node's right is null or not and return a 1? There's a way to consolidate this into just one logic here, meaning that this part could be simplified. If you look at this closely, we don't want to check when this condition is met, because I don't have my tree in a balanced way. Sometimes the tree could be lopsided. I don't want to compare my left and right. Maybe there's more right. There is no left. Writing this entire selection criteria is extra. So if you can just generically frame this entire problem as if null is null, return 0. And then said that cost of doing the business is to finding all of the left and all of the right. This is one recursive call. This is another recursive call. To recursively bubble up You don't have to worry about this. So version 2 could be simplified. So let's take a look at the simplified version of it, which is number 3. Checking to see if node is null or not. If so, return 0, otherwise return 1, plus the recursive call into node's left subtree, and a recursive call into right subtree. And that would get you the total number of nodes inside this tree. This is the most efficient way of going about the business, finding out the size of the tree using a recursive algorithm. Now, there's a drawback for this. Now, say if the tree has millions of nodes in there, obviously you don't really want to do this. Recursive to the left and recursive. This presents a lot of challenges. Every single call into that particular function requires some stack memory space because you have to keep track of where this function is. This is the value of backtracking, right? Backtracking requires some memory holding power. You do not want to do this at runtime when this height of the tree exceeds certain amount. Let's just move on to the regexec code. This is the translation of what we talked about from pseudocode into the actual code. Let's move on to the next one. This iterative version allows you to write for loop, just iterate through every single level. If you want to iterate through every single level of the tree using the level order, which is the breadth first search that we talked about earlier, or you can use depth first search, DFS or BFS. They use iterative methods. So this is one example of the breadth first search using the link stack. Last in, first out. We keep track of the left and then keep track of the right in that order. If you're using the Java implementation of stack, there is what we call peek. And the pop itself, what we call poll, P-O-L-L. Once you invoke this method, what you get is the number of counts, number of nodes. At every single point, instead of printing the value out, we're counting by 1, starting with 0, as long as root is not null. So the entire mechanism is the same as what we had before. This methodology might be a little more expensive than the previous one because now we incur this extra stack. Using recursion, we don't need another ADT, but using this, we require the use of another ADT. Recursion sometimes could be very fast if the level is low, that you don't have to recurse into thousands of levels. Whereas using iterative methods, your stack is just going to keep growing and shrinking, growing, shrinking. There's the use of extra memory space. And this extra memory space is in a heap. So it's slightly slower than what you would in a stack. These are memory stack, memory heap, not data structure. Let's do some quick comparisons here, recursion or iteration. So generally speaking, as a rule of thumb, if your tree is small, you don't want to get into a recursion that goes on to hundreds of thousands. So if the recursion is relatively shallow, meaning the tree height is very low in number, yes, you could just use a recursion. And recursive solution is clean versus, as you saw in a BSD implementation, where the entire logic is pretty inundated. At that level, it's harder to maintain efficiency in time and space. What about time? If the level is short, meaning it's shallow, then time-wise, recursion could be just as fast as iterative, and then you want to consider recursion. The other one is space. Well, if space is not really an issue, meaning you have sufficient runtime stack memory, then that may put recursive version to be on the advantageous side versus an iterative method.